Okay, optimization example 8. Again, don't forget to try these first before you check your work with these videos. All right, example 8 says determine the points or point on y equals x squared plus 1 that are closest to 0, 2. All right, this is like the least information we've been given in a problem. So where do we start? So our answer is going to be some points. I'm going to go ahead and state that. All right. The points on y equals x squared plus 1 that are closest to 0, 2. And I don't know if it's going to be 1 or more. They put that S there, so I am taking the hint that it's going to be plural. If it's singular, we can fix that later. Well, I'm going to leave some space to put more points if we need it. All right, so this is what our answer is going to look like once we find that point or points. So we're looking for coordinate pairs. So looking at the graph that they give us, all right, so we've got our function y equals x squared plus 1. We've got our point 0, 2. So we're looking for some point. I'm just going to draw like an arbitrary point over here. That is closest to 0, 2. All right, I'm actually going to draw it. I don't know where it's going to be. Somewhere over here. And that point is going to be coordinates x, and the y value is x squared plus 1. Okay, so whatever those x values are, it's got to follow that pattern. Okay, so what are we trying to maximize or minimize? So it says closest, so that means we're trying to minimize distance. All right, so I want us to read that closest as minimizing distance. Okay, and in this case, it's between 2 points, right? A point that we're given, 0, 2, and a point on our parabola here. So distance between 2 points, we have a formula for that. A while since I've used this, but I think that's our distance formula. So the square root of the difference of our x's squared plus the difference of our y's squared. Okay, so we need our 2 points. So what if we call this 0, 2? What if we call that our first point, x1, y1? So that means our second point is going to be whatever this point is on our curve. So I'm going to call this x2. This is our y2. And we've got 4 variables in here, but if we sub in these points, I think we can rewrite it so that only our x2 or our x is our only independent variable. So are there any restrictions for x? Any constraints? I mean, we can see from the picture that it doesn't make sense for it to go way up here. Points up here are going to be way farther than points in this region. So I'm expecting some answer between whatever, -1.5, maybe even -1-ish to +1, but I'm not sure. So I don't see any constraints for x for now. All right, so let's see what we can do. Let's sub in our values here for D. Let's try that again. Okay, so we said x2 is just going to be x2. I think later we can just replace that with x when that's the only variable. Minus, and then our x1 is 0 from that given point. y2, that's our x squared plus 1. Minus, and then our y1 is 2. Okay, now we've got a distance equation in terms of just one variable. I think I'll go ahead and just for the sake of simplicity, get rid of those sub 2's. I'm gonna just have to remember that when I find my x, I know that this is where I'm gonna plug it into. Okay, here and here. Okay, so let's simplify. Still got a square root. X minus 0 is x. X squared is just x squared. What do we got here? I'm going to keep this in parentheses. I've got x squared minus 1. Quantity squared. Let's see. There's our distance formula. In order for us to take the derivative of that, I think I'm going to want to multiply this out. I don't think we're going to be able to get rid of this square root part. Actually, I might rewrite it as to the 1/2 power. But let's simplify this. This is going to be x to the 4th minus 2x squared plus 1. Okay, ooh, I'm glad I did that. Now we can combine these x squared terms. So that's going to be x squared minus 2x squared is just minus x squared. I'm going to put my x to the 4th up front, just keep it in standard form, and then plus 1. And then all that in place of our square root is being raised to the 1/2 power. All right, let me check my work before I go forwards. Yeah, feel good about that. All right, so there's our distance formula. So now, again, we're looking to minimize distance. So this is our optimization formula. So we want to go ahead and take the derivative of this. All right, so let's find d prime. We've got 1/2 times everything on the inside to the negative 1/2 power, and then let's do our chain rule. Make sure we use parentheses, times 4x cubed minus 2x. That's it. All right, I'm going to rewrite that. We've got definitely going to have a fraction. We've got 2 in the denominator. We've got this square root that's going to be in the denominator. But this is still in our numerator. So 4x cubed minus 2x. Okay, so we have our derivative. Now, the reason why we did that, because we want to find our critical point. So let's find where, I think we're going to need some space for this, where d prime equals 0 and d prime undefined. All right, we've got a nice rational function here. So we can take that numerator, set it equal to 0. And we can take the denominator, set it equal to 0. To find those values there. Okay. Let's see. For this first one, this cubic, I don't like this cubic, but I can factor out 2x from that. So that leaves me with 2x squared minus 1. So that gives me x equals 0. And if we were to solve this, add 1, divide by 2, and square root it. Add 1, divide by 2, and square root it. We're going to need to consider the positive and negative square root of 1/2, which is root 1 is just 1 over root 2, and that is square root of 2 over 2. Multiply top and the bottom by root 2. feels very trig-like. Okay, so we got 3 critical points from setting it equal to 0. So let's see how many we get from undefined. That's the most critical points we've had so far. All right, divide both sides by 2. That's just going to be 0. Square both sides. X to the 4th minus x squared plus 1 equals 0. That is a 4th degree. Let's go to our calculator for that one. Not sure we're going to get any solutions from this, but let's try. Okay, so let's clear out anything we have in y1. And what are we putting in there? X to the 4th minus x squared plus 1. X to the 4th minus, oops. X to the 4th, get out of that x, what just happened? Struggling. Minus x squared, is it plus 1? Plus 1. Okay, for my x values, let's go again. Like we said, I think 2 is as far as we need to go. Numbers outside of -2 and 2 feel like they're just going to get further and further away. I don't think those are going to make sense outside of there. All right, let's graph it, see what we get. Okay, so it's a 4th degree function. So I was kind of concerned about this. So it doesn't touch it anywhere, right? We can, if we want to be like, well, does it? Are the pixels just playing with us? We can go down to our y min, and we don't need to go that low, and we don't need to go that high. So if we zoom in a little bit, yeah, it does not touch the x-axis anywhere. So nowhere is our d prime undefined. But we've got 3 from over here, so we've got our work cut out for us. So sign chart. Make sure you put them in the right order. Excuse me. And we're looking at what does d prime tell us about d. This is a cubic with a positive leading coefficient. I think we're going to need to do test points. Negative root 2 over 2. Let's see. Root 2 is like 1 point something. So that's approximately -1/2. So let's go -1 as our test point to the left here. I'll change color again. So if I plug in a -1 into d prime, then I'm going to get -4 plus 2. So that's going to be, am I plugging that in the right spot? Oh, I got to plug it in everywhere. Well, I guess we don't. We don't have to. Just know that this is going to be negative on top. We're just looking for the sign. In our denominator, when we take the square root, it's got to be positive times another positive. So actually our denominator is always going to be positive. So that's nice. We can just look at the numerator there. Okay, so that's going to be negative. So that means our distance is decreasing up until that point. And then let's look between these two. Ooh. What are we going to pick between these two? I don't know. Negative. Honestly, we could have. Did we put d prime? Oh, we put d prime into our. No, we just put the denominator in. Damn it. Wait. Yeah. We could put it into our calculator. Tempted to, as opposed to, we can plug it in. All right. That's before I make up your mind. Negative. How about negative 1/10? Doesn't matter. Negative 1/10 cubed is going to be -4 over 1/10 cubed is 1,000. plus 2 times 1/10. That is definitely going to be positive. 2/10 is way bigger than negative 4,000. So that's going to be a positive over a positive. So that's going to be increasing. To the right of 0, if we were to just plug in a positive, then this one would be positive and this one would be negative. So that's going to be a negative because that 2/10 is bigger than 4 thousandths by a long shot. And then if we plug in a point to the right of root 2 over 2, for time's sake, it's going to be positive. Again, plug in 1/2 or graph the whole d prime and see those sign changes. And again, if you plugged in d prime way back when and found these values, round them to the nearest thousandths, that's fine. Totally fine. The directions don't say either way. So why do we do all that? We did all that so that we could verify which critical points are our extrema. It turns out there's a sign change at each one. They're all extrema, but which one are we looking for? We're looking to minimize distance. All right, this is, I think, the first example we've looked at where we've got more critical points than we do solutions. So we really need our sign chart here. Okay, so we're not going to have 3 solutions, 3 points. We're looking for minimum. So when sign changes from negative to positive on your derivative, you've got a minimum. So I'm going to just state minimum at x equals, and there's one both at positive and negative root 2 over 2. Since d prime sign change from negative to positive. So at 0, there's a maximum. On this interval, so it's actually further away than anything between 0 and root 2 over 2 in either direction. But then outside of that, notice how, just like we can see on our graph, outside of that, that distance increases this way, and going left, even though that says decreases, that's if we're going to the right. So if we flip script and go to the left, that makes sense. The distance is getting bigger as we go further away in the negative direction. All right, good. So that means our x values are negative root 2 over 2 and positive root 2 over 2. We still need to find our y values. So let's plug that into our x squared plus 1. Where can we do that? Y equals x squared plus 1. Let me get rid of this x here. We didn't use that. Okay, square that. We get 2 in the top, 4 in the bottom, plus 1. That's just 1/2. Plus 1 is 1 1/2. Boom. So those are our y values for both, because if you square a negative, you're still going to get a positive. So we did have 2 points. And again, those are going to be, I don't know, a little bit bigger than 1/2 over up 1 1/2. So actually, I was pretty close to my arbitrary point. This guy here will give us that minimum distance d there. Hope that helped.